Good afternoon, panel members. My name is Joe O'Donnell, and my project is titled Inconspicuous. With an aim to reduce motorcycle-related incidents by improving rider detection, the project saw the development of the Motorcycle Alert Proximity System, or MAPS, which will be explored later within the presentation. The project has stemmed from an accident I experienced earlier this year, similar to the one you just watched, where a driver failed to register me. In my instance, someone pulled in front of two vehicles sitting in standstill traffic and unfortunately collided with me, who was filtering through. This experience triggered my interest in motorcycle safety and hence the research and development of my project. My research began by exploring motorcycle accident statistics in Victoria and found that collisions like mine were incredibly common. A 2015 TAC report found that 44% of motorcycle accidents involved another party, with failure to give way from another vehicle accounting for 30% and another vehicle changing lanes accounting for 29%. These clearly illustrate a conspicuity issue whereby motorists are simply failing to register and consider motorcyclists when making critical decisions. My research also revealed how increasingly necessary advancements in motorcycle technology is, with motorcyclists representing 18% of lives lost and 17% of hospitalised claims on Victorian roads alone, despite only making up less than 1% of the total travelled kilometres covered by Victorian registered vehicles. These statistics were found within the Discover phase of the Double Diamond Framework, which was utilised for this project to systematically structure the thinking and allow for the development of an effective outcome. Semester 1 saw the Discover and Define phases, whilst the second semester saw the Develop and Deliver phases, providing a scaffold for intentional and focused research by exploring an issue more widely and deeply through divergent thinking, and then taking focused action through convergent thinking. With a clear problem at hand, I engaged in design methods including publications research, benchmarking, and interest groups to generate a more in-depth understanding of the motorcycle conspicuity field, including the cultural and societal expectations relevant to the differing rider demographics. An analysis of past, present, and future precedents was conducted, indicating a gap for design intervention. High visibility gear, for example, is a common and effective strategy, but challenges the rider culture and therefore is often dismissed. Riders simply refuse to wear high visibility as it stands to oppress the cool identity they wish to portray, whilst also carrying connotations of inexperience. Daytime running lights also presented opportunities for configuration redesign, as their effectiveness has dropped significantly since their application on all standard vehicles. These findings and the intention of trying to produce a marketable product by the end of semester 2 guided my definition stage by focusing on finding ways to improve the perception of high visibility to riders and incorporating a daytime running light element. However, over the mid-semester break, with more and more evidence stacking up against the effectiveness of these options, I shifted the direction of my project to a more speculative approach, focusing on what technology is becoming more available and accessible. This comes as contemporary riders are sharing a more common worry for driver distraction. Reliance on mobile phones, particularly in the younger demographic, is raising far more concerns for rider safety. To further support this, I conducted a survey which asked participants to outline their biggest fears when riding and the strategies they engage with to prevent accidents. The responses included unpredictable driving by other motorists, distracted drivers, and a motorist not seeing me. Responses also described high-vis gear as being uncool or unappealing and ineffective, ultimately validating the change in direction. Research into future motorcycle detection approaches was then conducted, revealing two main solutions: advanced driver-assisted systems and vehicle-to-vehicle communications, both of which provide significant development towards safer roads, but have their own disadvantages and drawbacks. Advanced driver-assisted systems are limited in range and require full vision for motorcycle detection, whilst also only being available on newer generation vehicles. Vehicle-to-vehicle communication has the greatest potential, but has not seen any breakthroughs, as no vehicle manufacturer is happy to commit to the technology due to the lack of security around the frequency at which it will operate. With this technology available but underutilized, I saw an opportunity for design of a simpler system which improves rider safety and functions off the existing infrastructure of other services. The Motorcycle Alert Proximity System, or MAPS, is a GPS module that communicates with surrounding navigational services such as Google and Apple Maps, alerting drivers when they are within a calculated proximity to improve their detection and ultimately reduce the chances of a collision. The design development for this project was split into a number of elements: the notification alert system, which drivers engage with, an electronics package to validate the theory behind the project, a module housing for riders to install into their motorcycle, as well as an application which allows for increased functionality and security. Firstly, the notification alert system, which operates through various navigational services, was developed. With the intention of the system to act as a plug-in for other services, the notifications were required to deliver clear and concise information to drivers without causing emotional distress or distraction. Concepts were generated and then evaluated before refined versions were visualized on a live mapping service. A distinctive audible alert was also paired with the system to help establish a Pavlovian response and assist in the push notification function, which will operate for drivers who aren't actively engaging in their navigational service. The following is a couple of basic examples of the live map testing of the refined versions. The electronics package involved some basic level proof of concept with an Arduino board coded and assembled to provide location and accelerometer data. With greater resources, a software engineering team could develop and code for a fully functioning package that would operate as intended. The requirements include a cellular GPS module with an effective antenna to reduce latency, an accelerometer to allow for improved power consumption through a sleep mode, and an independent power supply, which is expected to have 3 to 5 years of life as achieved by other similar GPS module products. The housing module development involved iterative sketching, computer-aided design prototyping, and visualizations. An initial prototype was designed to house the electronics package created in testing, which was 3D printed and was able to validate the installation. As mentioned before, with more resources, a function-specific printed circuit board with a custom power input could be developed to allow for a smaller housing. An educated calculation was made that allowed for a development of a refined version of the housing, which could more greatly reflect the actual size of the product. The final outcome saw a robust housing module and thorough notification alert sequence. A comprehensive algorithm was also developed to perform the appropriate calculations of when to inform the driver of a rider based upon the change in velocity between the motorcycle and car. Navigational systems will only assess maps signals within a kilometre radius of the vehicle to reduce battery consumption. Once the motorcyclist triggers the proximity function, the navigational system will then engage the notification alert unless the motorcycle exits this kilometre radius. Once alerted, the motorcycle will then also remain on the navigational unit until it is outside the kilometre radius. Additional warning tones will be sent after every 5 minutes if the motorcycle remains within the driver's proximity. The following is an example of how the system would function in the scenario presented at the beginning of the presentation, illustrating installation and the driver interface. An application has also been developed which improves the functionality of the product service system by allowing users to observe the battery levels and view their riding history. The application also ensures security and prevents people exploiting the product as it requires two-factor authentication through vehicle registration and VIN number for activation. Future applications and iterations of the product could see a crash detection system to inform emergency contacts of an accident, and expanding the product functionality for other vulnerable road users, such as bicyclists. In summary, the MAPS product has been designed with the intention of reducing motorcycle-related accidents across varying scenarios, whilst also meeting the needs of its users by providing a virtual high visibility that doesn't compromise identity and culture. By achieving this, MAPS will ultimately see lives saved and reduction in road trauma. Thank you for listening to my presentation.